The vector dot product formula. Given vector A is x1, y1 in component form and vector B is x2, y2, then the dot product, vector A dot vector B, is equal to x1, x2 plus y1, y2, which equals the magnitude of vector A multiplied by the magnitude of vector B multiplied by the cosine of the non-reflex angle between the two vectors. The dot product is the product of the magnitude of the vectors in the same direction. And here's an example diagram. There's vector A, there's vector B, and there's the part of vector A that is traveling along the direction of vector B, which is A cos theta. Hence the dot product, vector A dot vector B, is equal to the magnitude of vector A multiplied by the magnitude of vector B multiplied by the cosine of the angle between the two vectors. The vector dot product formula is based on the cosine rule. Let vector OQ be x1, y1 and vector OP be x2, y2 when expressed in component form. Now point Q has coordinates x1, y1, so that's this point here. And point P has coordinates x2, y2, which is this point here. So they correspond to the arrowheads of both of these vectors. Now joining PQ, we then complete triangle OQP and we can apply the cosine rule. And we'll define angle theta as the angle between vectors OQ and OP. So I'm going to treat OQ and OP now as intervals, and PQ is the interval that joins P and Q. Now by the cosine rule, PQ squared is equal to OQ squared plus OP squared minus 2 times OQ times OP times the cosine of the angle between OQ and OP. Now the magnitude or the length of PQ is given by x1 minus x2 all squared plus y1 minus y2 all squared. And that equals to OQ all squared, which is x1 squared plus y1 squared, plus OP squared, which is x2 squared plus y2 squared, minus 2 times the square root of x1 squared plus y1 squared, multiplied by the square root of x2 squared plus y2 squared, multiplied by cos of theta. Now expanding the brackets on the left-hand side, and there will be some cancellation as well between the left-hand side and the right-hand side. So expanding the left-hand side, we have x1 squared minus 2x1 x2 plus x2 squared plus y1 squared minus 2 y1 y2 plus y2 squared is equal to all of this. And we can cancel x1 squared from the left-hand side, x1 squared from the right-hand side, x2 squared from the left-hand side, x2 squared from the right-hand side. There's a y1 squared and a y2 squared that can get cancelled as well. And we can also divide both sides by -2. So what we end up with on the left-hand side, or what's left over, is x1, x2 plus y1, y2 is equal to the square root of x1 squared plus y1 squared multiplied by the square root of x2 squared plus y2 squared multiplied by the cosine of theta. And the square root of x1 squared plus y1 squared is the magnitude of vector OQ, and the square root of x2 squared plus y2 squared is the magnitude of vector OP. So x1, x2 plus y1, y2 is equal to the magnitude of vector OQ multiplied by the magnitude of vector OP multiplied by the cosine of theta as required. The dot product can be used to determine if two non-zero vectors are either parallel or perpendicular to each other or neither. Let vector A be x1, y1 and vector B be x2, y2 expressed in component form. Now given vector A is parallel to vector B, then theta, the angle between the two vectors, is equal to 0 and cos of 0 is equal to 1. Hence the dot product, vector A dot vector B, is equal to the magnitude of vector A multiplied by the magnitude of vector B. Now given vector A perpendicular to vector B, then theta is equal to pi over 2 and cos of pi over 2 is equal to 0. Hence the dot product is equal to 0. Given theta obtuse, that is theta greater than pi over 2 and less than pi, cos of theta is less than 0 or negative, hence the dot product will be negative. We'll go back to the case where the two vectors A and B are perpendicular to each other. So using the dot product formula, x1, x2 plus y1, y2, if the two vectors are perpendicular to each other, the dot product will equal 0. So x1, x2 plus y1, y2 equals 0. Subtracting x1, x2 from both sides of the equation, we have y1, y2 is equal to negative x1, x2. And dividing both sides of the equation by x1, x2, we have y1, y2 over x1, x2 is equal to negative 1. And expressing the left-hand side as a product of two fractions, we have y1 over x1 multiplied by y2 over x2 is equal to negative 1. Now, relative to the Cartesian plane, y1 over x1 is the gradient of vector A, and y2 over x2 is the gradient of vector B. You may recall the formula, m1 multiplied by m2 is equal to negative 1 if the gradient m1 is perpendicular to the gradient m2 and vice versa.